All right. And so we finished out, or we finished a couple problems looking at the p-value, some p-value examples. I also wanted to then say, okay, we can actually use the critical value approach as well. So I'll kind of set up the p-value and critical value approach. So we already thought about p-values. We can also do something called critical values. Right? So here, with a critical value approach, we'll still calculate our test or our z statistic, but we're also then going to have a critical value that matches up with whatever alpha we're setting. We're then going to compare that critical value to our test statistic. If our test statistic is larger in absolute value, or we'll create these things called rejection regions. If it's in our rejection region, then we reject the null. If it's not, then we fail to reject the null. Right? So where this rejection region is depends on the type of test, right? Or what's in the alternative hypothesis, and also what level of confidence we're choosing. Okay. So here I've got kind of a summary, but I think I can kind of give you some better visuals of what these confidence interval or what these critical values will look like. So let's skip ahead a little bit. Here we go. So what is a critical value, right? So if I'm thinking about if I've got the z value of 1.5, or sorry, 1.65, I know the area to the right of it is 0.05. Right? So I know that if I ever see a z statistic that is larger than 1.65 here, then the area to the right of it, its p-value will be smaller than alpha, right? So I'm going to find these critical values where I say, okay, look, if I'm doing a 95% confidence test interval, 5% significance level, I know that any test statistic that's greater than 1.65, I'm going to have a p-value that's less than alpha, or I should be rejecting the null, right? So what I'm thinking about there is for this right-tailed test, I'm going to go a certain number of standard deviations away that gives me alpha in the tail, and then say, okay, anything to the right of that for a right-tailed test, if I find a test statistic that's in this range, it will have a p-value smaller than alpha, so I should reject the null. Now, if I have a left-tailed test, then evidence on the left side, right, less than the assumed true value is going to go against the null. So there, I'm looking at that z value that will give me alpha in the lower left tail, and my rejection region is anything to the left of it. So notice for a left-tailed test, because my normal distribution is centered at 0, I'm always going to have negative critical values. For a right-tailed test, I'm always going to be looking at to the right of the mean is 0, I'm always going to have positive critical values. And then for a two-tailed test, right, this was, we have a tail on each side. So I'm now looking for the z value or the number of standard deviations away I need to go to get there to be half of alpha in each tail. So it's going to be two critical values, same number, just one positive, one negative. And then if I see a test statistic anywhere here or anywhere here in the screen range, I would reject. Okay. All right, so we'll go back. I just want to do things out of order sometimes, but there's a reason why, right? So um, I've got my greater than test. So there I'm looking at that right tail test. We said anytime the test statistic is greater than my critical value. Left tail test, anytime my test statistic is less than, right, my critical value. Um, and there it's basically a larger negative number. And then for a two-tailed test, I don't want to get worried about signs. And in fact, I could do this for all of these examples. I could always just take the absolute value. If the absolute value of my test statistic is greater than the absolute value of my critical value, I can reject. Now, that won't always be the case because if I find evidence that supports the null, I can't do that for my left and right tail test, which is why I kind of have it set up like this. Only kind of thinking about that absolute value when I'm looking at a two-tail test. Okay. All right. So, we're going to be finding the same values, right? Anytime I have a one-tail test, the z value that gives me 0.1, 0.05, and 0.01 in the left tail, right? How could I find those? Well, 0.1 is going to be in between here. So negative 1.28, negative 1.29, 1.29, 0.05, going to be right here. So negative 1.64, negative 1.65. That's where I'm getting these values. Now for a right tail test, because this is a symmetric distribution, if I want that same alpha in the right tail, it's the exact same values, but positive. And then for a two-tailed test, I wouldn't be looking up alpha. I'd be looking up alpha divided by 2, right? So here, my critical value for a two-tailed test, I don't just have one, it's critical values, 1 point and positive, negative 1.65. So notice my critical values for a two-tailed test at the same confidence level or significance level is different from a one-tailed test. Okay. So, we still conduct our test statistic. I say conduct our test statistic. We still calculate our test statistic the exact same way. We still talk about rejection the same way, right? Whatever alpha is, we're rejecting the null hypothesis that times 100% of the time. We kind of already went through how do I find these critical values. Here's outlines the critical value approach. So determine the null alternative, figure out what level I want to do this hypothesis test at, my alpha, calculate my test statistic, use the type of test and whatever alpha is to find my critical value and my rejection region. If my test statistic is in that rejection region, then I can reject. Right? All right. So I think with this, I think working through more of these is just going to help make a little bit more sense. So we're going to go back to an example that we already did with the p-value approach. So we'll kind of see that these two approaches will lead us to the same conclusions. Okay. So here I had, I want to know, is that mean retirement age greater than 67? So I assumed the opposite was true, which is that it's less than or equal to. I know if what I assume to be true is in fact true, my sample means should be centered around that true population mean. Now here's just the assumed value, but if it was true. I then found a sample mean of 71, right? We said, okay, I could turn that into a test statistic, find the area to the right, that would represent my p-value. I think when we did this, it was 0.0132, right? So I can kind of prove this to myself, or here, let's see. So I've got, I think this ends up being 2.22, right? So how did we find that test statistic? We took our sample mean, subtracted the assumed true mean, divided by square root of our population variance, which was 81, divided by our sample size, which was 25 people. Get 2.22, look that up in our standard normal table or using Excel, and that's where we got that p-value of 0.0132. Okay. It's less than the alpha of 0.1 and 0.05, so we would reject at those two levels, not less than 0.01, so we would fail to reject. Now, if I use a critical value approach, what I would actually do is say, okay, look, if I wanted to find the critical value for these, I actually would have 3 different critical values and rejection regions. Okay. Now, I'll show you in a second. So how do I find those critical values? Well, it's going to be the z values that give me 0.1, 0.05, and 0.01 in my right tail. So what I can do in practice is I can look up those 3 alpha values of 0.1, 0.05, and 0.01. So if I do that, so 0.1 is going to be what? 1.28, 1.29. Look up keep looking up each. Now, they're always going to be the same. It's always going to be these same 3 values. So if I'm thinking about, here's my 3 critical values, really what that's saying is, okay, look, 1.29 is going to be my critical value associated with an alpha of 0.1. 1.65 is going to be my critical value associated with 0.05. And then 2.33 is the critical value associated with 0.01. Here's my 3 rejection regions. My test statistic notice is in the rejection region for that 10% significance level or 90% confidence. It's in the rejection region for the 95% confidence or 5% significance level, but it's not in my rejection region at the kind of 1% significance level, which notice that's the exact same decisions that I made using the p-value approach. Okay. Okay. Let me think here what I want to do. I want to point out 2 other things, and I'll use this example to do so. So if I think about this test, so saying, okay, look, let's say I had this, whoops, as my null and alternative hypothesis. So I'm assuming that the null is less than or equal to 67. Why then am I not using 66? Because that's a value in that range. So the idea here is if I use that cutoff value that I find in the null and alternative, any sample evidence I see that goes against that null, if I calculate this p-value, let me go through and do it. I think we said it was what, 0.0132. Notice if I were to use any other assumed true value, so let's say I use 66, well, then my sample means would be normally distributed around that value. But notice, if now I'm assuming it's 66, finding the same sample mean, that evidence is going to be even further from the assumed true mean, which means my p-value is going to be even smaller now. So if I can reject 67, I know that I can reject every other value in that range. Okay? So that's why we only use kind of the cutoff value there. Okay. The other thing I wanted to point out is kind of try to make this connection between our p-values and our critical values. So once I turn these into test statistics, and I'll do a right-tailed test just for the sake of this, whatever my critical value is, it's associated with a specific alpha, right? So here, this critical value, the area to the right of it is whatever alpha is. My p-value, well, that is lining up with, okay, what is my test statistic or what is my z statistic? And that z statistic, the area to the right of it, that's my p-value. So the reason why they both give me the same decision is because if I'm comparing this critical value and the test statistic, anytime this test statistic is greater than my critical value, notice what's happening to the area to the right. Anytime the test statistic is greater than my critical value, that p-value will also be less than alpha. So it's really just like I'm comparing I'm just comparing like 2 different sides of the coin. I can either compare the z values, so notice critical values still represent a z value, or I can compare the area under the curve and the tail. But those 2 things are directly related. So it doesn't matter which way I do, I can always kind of find the same thing. In fact, just to kind of line this up for you as well, I could even think about this as a 2-tailed test. So let's say I found my critical values for alpha over 2, right? It's going to be the same value, but one's going to be positive, one's going to be negative. That's going to give me a total of alpha in the tails, right? Once I find my test statistic, this is going to be a test statistic or a z statistic. The area to the right of it, it's going to be associated with half my p-value, which is why when we're using the p-value approach, we actually took this area and multiplied it by 2. Right? But same kind of idea. If I find a test statistic on either side, right, that's greater than an absolute value or like a more higher in magnitude than my critical value, then the area to the right of that is going to be smaller than alpha, right? Or my p-value, sorry, area to the right and left of that would be smaller than my alpha, okay? So it doesn't matter which approach I use, I should end up with the exact same decisions. Okay. All right. So where are we at? We talked about this. I worked through this example for us. We went through, found the test statistic. It's in the rejection, or sorry, found the test statistic critical value. It's in the rejection region. So we reject. Let's do a slightly different one. Right? So let's say I'm looking at what's this? Back to school spending. So some trade group says that the average back to school spending is $606. Right? I get a sample of 30 families, and I find a sample mean of 622. It's known that the population variance is 4,000. So the whole thing I want to test is the average back to school spending different than this amount that the trade group put out? So is it different than $606? So anytime I see this word different than, I should automatically be thinking about, I've got a two-tailed test. Okay. Because this different than, that is not equal to. So I'm saying, is that true population mean not equal to $606? I assume the opposite is true, which is that it's exactly equal to $606, right? So I've got my kind of two-tailed test here, right? What's the p-value of this test going to be, right? Well, what are the things I need? Well, I've already determined the null and alternative. I'm not using a specific alpha here. I'll compare to a bunch of them, so we can kind of skip that step for right now. Calculating the z, or the test statistic, I'll take that sample mean of 622, subtract the assumed true mean coming from my null alternative hypothesis, and then population variance, my sample size here. It's just a matter of plugging my things in, or plugging my values into that equation. And I'll give you a formula sheet where you have all these equations to look at as well. So I get a test statistic of 1.39, right? I'm then going to use this to find my p-value, but remember, it's a two-tailed test. So whatever area I find to the right of 1.39, I need to multiply it by 2. So I can do this one of two ways, right? I could go to my table here, 1.39. So 1.3, if I can follow this right, 9.9177. Now that's not going to be the area to the right, that's the area to the left. So I need to subtract that from 1. So 1 minus 0.9177 would be what? 0.0823, if I'm doing math in my head correct. And in fact, I can double check this by, oh, well, s.dist 1.39 was that z value. However, that's going to give me, oh, I need to make it cumulative, sorry, I'm a 1. So 0.9177. Oh, I said, but I still want the area to the right, so I need to subtract it from 1. 0.0822, right? But that's just the area to the right of positive 1.39. So if I'm thinking about visually what this looks like, and I'm gonna chop off the decimals just to make it easier to write. So I think this was what? Assumed true value was 606. We found a sample mean of 622-ish, right? So once I turn this into a test statistic or a z-value, we got 1.39. I just looked it up. What was the area to the right of that? 0.0823 approximately. Right? However, remember we started out, this was a two-tailed test. So finding something that was 1.39 standard deviations above the assumed true mean, it was equally as likely I could have found something that was 1.39 standard deviations below that assumed true mean, and that's equally damning evidence against my null hypothesis. Right? So once I find this area to find my total p-value, I still would need to multiply it by 2. So here I end up with a p-value, it's like what, 0.1646, right? This isn't less than any of my alpha values, so I'm going to fail to reject at every single level. Now, what if I instead had done the critical value approach? So I could still set up the same way, but instead of doing this, I'm going to think about it a slightly different way. So here, I'm looking at my critical values. I want a pair of critical values that give me 0.01 total in the tails, or, right, 0.01 over 2 in each tail, right? I then want a pair of critical values for 0.05. I then want another pair of critical values that give me a total area in the tails of 0.1, right? So what am I going to do? Well, I could use the table, right, to find these. So, I mean, this is where like you don't always have to use the table for these standard normal vat examples. It's always going to be the same three values. Which if I do this real quick, so equal to norm dot s dot inv. What are the areas I want in the tail? Excuse me, 1 divided by 2, right? Alpha divided by 2. Norm dot s dot inv, 0.05 alpha divided by 2, and norm dot s dot inv, 0.01 divided by 2. Now, obviously, I don't want the negative sign here. I could use the absolute value or kind of my trick of 1 minus. Although here, technically, this is only one of my critical values. I actually, at every single level, so, oops, 90, 95, 99%. At every single level, I'm actually going to have a pair of critical values, right? Alphas were 0.1, 0.05, 0.01. Okay. So I'm going to put these on my graph. So there we go. So this was what? 1.64 or approximately 1.65, negative 1.65. This was 1.96, 1.96, 2.58, 2.58. You can think about here are my rejection regions. Okay. I'm then going to plot my test statistic, which we found before with 1.39. Where would that fall? Right here. Notice it's not in any of my rejection regions, so I failed to reject at every single level, which is the same decision I made looking at its p-value. Okay. So it kind of depends which way, you find easier p-value, critical value approach. I like this critical value just because it does have the visual where you can see the rejection region, is the test statistic in that rejection region. But either way, should lead us to the same answer. All right, so let's go back here. And keep moving. Oh, so here's kind of a summary of those two examples. We don't always have to compare to the conventional levels. Notice if I wanted to look instead at the 80% confidence level or an alpha of 0.2, well, then at that level, I can reject in both of the examples, but specifically the second one, I can reject. Right? So what are my critical values? I kind of already jumped the gun on this, but we looked them up. Anytime I have a two-tailed test, I'm going to have pairs of critical values. So right away, I know that I should be looking at C or D. If I forget that for a two-tailed test, I have to divide alpha by 2, right? I only want half of alpha in each tail. These would be the values I find. If I correctly divide it by 2, like we did and I showed you in Excel, and we used the table, these would be the values we find. Okay. So we already went through all of this. Failed to reject at all levels. Here's an example that's a little bit, a type of question you could see that's a little bit more tricky than what we've done up to this point. So, let's assume I have the same setup for this back to spending, school spending example, but I want to know, okay, what would the value, cutoff value be? So what would the very first sample mean be that if I saw it, I could reject the null at the 90% level? Okay. So I'm going to draw this out for a second, and then we'll kind of come back to answering this. So I want to know what's the very first sample mean I could see where I would reject the null. So I have my null is that it's equal to 606.4. Alternative is that it's not equal to that value. Okay. So if what I assume to be true is in fact true, my sample means should be distributed normally around that assumed true population mean, if it in fact is true. Now, what I'll do is say, okay, look, what's the very first test statistic that I could reject the null for? And I could look at either side here because it's a two-tailed test. Positive values are often easier to deal with, so I'm just going to use that side, and I'll kind of mention at the end how you could do it instead for the other way. But notice here, there is going to be some sample mean value that exactly hits my critical value, and I believe I had the 90% confidence level, so an alpha of 0.1. Any test statistic, any sample mean past that, any great sample mean greater than that, is going to end up then with a z statistic somewhere in this range, which would be in my rejection region, and I could reject the null. So the very first sample mean that I can reject will be or when you find out what the cutoff is whatever that critical value is. Right? So if I want an area of 0.1 in my upper right tail, I do this two ways. So the first way, I want 0.1 in my upper right tail. However, this table only gives me the area to the left. So if I want 0.1 in the upper right tail, that's really saying I want 0.9 in my lower tail. So 0.9 looks like it's, oh, why can't I find it? Oh my gosh, because I'm looking at the wrong one. 0.9. Here we go. So in between these two, so 1.28 and 1.29. So take the higher of the two, 1.29, right? Oh, but I made a mistake because I got caught up. What did this example have? We actually had oh, and now I don't know. Oh, here it is. We actually had a two-tailed test. So I don't want the critical value that gives me alpha in one tail, right? I want the critical value that gives me critical values that give me alpha total in my tails, right? Or 0.1 over 2 in each tail, right? So I actually want 0.05. So if I look that up, 0.05, well, if I want 0.05 in the upper right tail, the area to the left would then be 0.95. In between these two values, 1.64, 1.65. We'll use the higher of the two, or I could have used Excel. It's not the sheet that I wanted to pull up. You could have used Excel norm dot s dot b, right? I wanted 0.05 in my tail. This is a lot more precise. Right? So 1.645, we'll just use that approximation, okay? So 1.645 and negative 1.645 would be my critical values. So I know that if my test statistic ever is above 1.645, I'll be rejecting. So that cutoff, what sample mean would that correspond to? Well, if my z value was 1.645, well, my z value is equal to sample mean, subtract that assumed true population mean, variance over sample size. So here, it's a matter of plugging things in, right? So from that problem, I think I had, this would have been, so I'm looking for this. Here was 606.4. Variance was 4225, 25 families. Now it's just a little bit of algebra, right? So I'd multiply both sides by whatever this value is. Then I'd add 606 to get my sample mean, right? So kind of work through that just so we can kind of see the math, but it shouldn't be too tough. So So if I actually do this math first, I'm going to cheat. Not cheat, but I'm going to do this in Excel. So the square root of 4225 divided by 25 is 13. Okay. So I'm going to take 13, multiply, both sides by 13. That would cancel, right? If I multiply 1.645, once again, just to kind of show you how I would do this in Excel, I think it makes it easier. I'm taking, okay, 1.645 times 13. I'm then going to say, okay, well, I need to add 606.4 to both sides. So if I add 606.4 to that value, I end up with 627. So as soon as I see a sample mean that is 627.78 or higher, I know I'll start to reject the null. Okay. Oh, actually, sorry. I thought I double clicked this. I'll take that value I had before, add 606 to it. That gives me the 627. That's going to be the first sample mean I'll start rejecting the null at. And it could have been a very similar thing, but instead, I would have been using my negative critical value, right? Well, it's the exact same process. The only difference is there's going to be a negative sign on that 1.645. So what would that look like? Well, there I would take 13, multiply it by negative 1.645. I would then take that, add the mean of 606. So either of these, right? If I see a sample mean of 627.78 or higher, or 585.015 or lower, those are going to be sample means where I can reject the null, right? So I just found these cutoffs were about 627. And actually, sorry, I should draw it right here. And what was the other one? 585. So if I see a sample mean any greater than this, I'll reject. If I see a sample mean any lower than this, I'll reject. Okay. So that's how I can kind of work in reverse or back out the value, the very first sample mean I would need to see in order to reject this null hypothesis. Okay.